What cosmic voids tell us about universe structure? Empty space, vast regions containing almost nothing, volumes larger than 1 billion light-years across with barely any galaxies inside them. These are cosmic voids, and they're one of the most important yet least appreciated features of our universe. When we think about the cosmos, we naturally focus on what's there: galaxies, stars, planets, the bright and dramatic objects that capture our imagination. But in cosmology, what's not there can be just as revealing as what is. The empty spaces between galaxies aren't just boring gaps. They're fundamental features that tell us how the universe formed, how it evolved, and what invisible forces shape its structure. Today, we're exploring cosmic voids, what they are, how they formed, what they contain, and most importantly, what they reveal about the large-scale structure of the universe, dark matter, dark energy, and the physics that governs cosmic evolution. These vast, empty regions are like cosmic fossils, preserving information about conditions in the early universe and revealing patterns that span the entire cosmos. Let's venture into the emptiness and discover what it tells us. Discovering the cosmic web. To understand cosmic voids, we first need to understand the large-scale structure of the universe, what astronomers call the cosmic web. For most of human history, we thought the universe was relatively uniform. Stars were scattered randomly through space, with no particular pattern. But as our telescopes improved and we mapped more galaxies, a surprising structure emerged. Galaxies aren't randomly distributed. They cluster together in groups and clusters. These clusters connect through filaments, long chains of galaxies stretching across hundreds of millions of light-years. These filaments intersect at nodes where massive galaxy clusters reside. And between the filaments lie the voids, vast regions containing very few galaxies. The first hints of this structure came in the 1970s and 1980s when astronomers began systematic surveys measuring distances to thousands of galaxies. When they plotted these galaxies in 3 dimensions, patterns emerged. Galaxies traced out walls and filaments surrounding empty regions. One of the most famous early discoveries was the Boötes void, identified in 1981. This void spans about 330 million light-years across, a region so large that light takes 330 million years to cross it. Within this enormous volume, astronomers found only about 60 galaxies, whereas a typical region that size would contain roughly 2,000. The Boötes void wasn't unique. As surveys expanded, astronomers found voids everywhere. They're not rare anomalies. They're a fundamental feature of cosmic structure. In fact, voids make up about 80% of the universe's volume. Most of space is empty space. This discovery revolutionized cosmology. The universe isn't uniform. It has structure on the largest observable scales, and this structure tells a story about how the universe evolved from the smooth plasma of the early universe to the web-like pattern we see today. How voids form. Cosmic voids form through gravitational evolution, and understanding their formation reveals fundamental physics. Start with the early universe. Shortly after the Big Bang, matter was distributed almost uniformly, but not perfectly. Tiny quantum fluctuations during cosmic inflation created regions that were slightly denser or slightly less dense than average, variations of only about 1 part in 100,000. These tiny fluctuations were the seeds of all cosmic structure. Slightly denser regions had slightly stronger gravity. They attracted surrounding matter, growing denser over time. Meanwhile, slightly less dense regions lost matter to their denser neighbors, becoming progressively emptier. This process is gravitational instability. Dense regions collapse under their own gravity, pulling in more matter and becoming denser still. Underdense regions expand faster than the cosmic average, becoming even less underdense as matter drains away toward denser regions, leaving voids behind. The process is somewhat like soap bubbles. When you blow soap bubbles, the soap film collects at the boundaries between bubbles, while the interior remains empty air. Similarly, in the universe, matter collects at the boundaries between voids, forming the filaments and walls we observe, while the void interiors remain relatively empty. Computer simulations confirm this picture. When cosmologists simulate the universe's evolution starting from early density fluctuations and letting gravity work for billions of years, the result is a cosmic web structure remarkably similar to what we observe: filaments, walls, clusters, and voids. The fact that simulations match observations validates our understanding of gravitational physics, dark matter, and cosmic evolution. Voids aren't mysterious anomalies. They're exactly what we expect from gravity acting on initial density fluctuations over cosmic time. Anatomy of a void. What's actually inside a void? The answer is not quite nothing, but close. Voids are defined as regions with significantly lower galaxy density than the cosmic average, typically containing less than 10% the normal density of galaxies. The largest voids contain only a handful of galaxies spread across hundreds of millions of light-years. But voids aren't completely empty. They contain, first, sparse galaxies. These void galaxies tend to be small, dwarf galaxies rather than large spirals or ellipticals. They form from the limited amount of matter present in the void. Studies show void galaxies are younger on average than galaxies in denser regions, suggesting star formation continued longer in the low-density void environment. Second, intergalactic gas. The space between galaxies isn't perfect vacuum. There's diffuse gas, primarily hydrogen, at extremely low density, typically less than 1 atom per cubic meter. This intergalactic medium is invisible to optical telescopes, but can be detected through its absorption of ultraviolet light from distant quasars. Third, dark matter. Although voids are underdense in dark matter compared to filaments and clusters, dark matter is still present. It forms the gravitational framework even in underdense regions. Simulations suggest voids contain dark matter at perhaps 20 to 30% of the cosmic average. Fourth, dark energy. This is where voids become especially interesting. Dark energy, the mysterious substance driving cosmic acceleration, has constant density everywhere, including in voids. While voids are underdense in matter, they're not underdense in dark energy. This means dark energy's effects are relatively more important in voids than in dense regions. The boundaries of voids aren't sharp walls. There's a gradual transition from the void interior, where galaxy density is very low, through the void wall, where galaxy density increases, to the filaments and clusters beyond. Voids are best thought of as regions of lower than average density, rather than regions of zero density. Voids also expand. As the universe expands overall, voids expand faster than average because they contain less matter to slow the expansion through gravity. This means voids grow over time, becoming emptier and larger as they mature. Void statistics and hierarchy. Voids come in a range of sizes, and studying their distribution reveals patterns. The smallest voids are just 30 to 50 million light-years across. Medium voids range from 100 to 200 million light-years. Large voids, like the Boötes void, extend to 300 to 400 million light-years. The largest known voids reach 500 million light-years or more. There's a hierarchy. Small voids are more common than large voids, following a statistical distribution similar to galaxy clusters. Many small ones, fewer medium ones, rare giants. This distribution isn't random. It reflects the spectrum of density fluctuations in the early universe. Cosmic inflation predicts a specific pattern of fluctuations across different scales, and the distribution of void sizes provides a way to test these predictions. Voids also tend to be roughly spherical or ellipsoidal. This shape results from gravity pulling matter inwards symmetrically from all directions at the void boundary. However, voids aren't isolated spheres. They connect to other voids, forming interconnected networks of underdense regions.
The void network accounts for most of the universe's volume. If you picked a random point in space, you'd most likely find yourself in a void, not in a filament or cluster. Galaxies, where stars, planets, and life exist, occupy a small fraction of the total volume, concentrated in the nodes and filaments. Studies of void statistics constrain cosmological models. The abundance and sizes of voids depend on parameters like matter density, dark energy density, and the nature of dark energy. By measuring void properties in large galaxy surveys, cosmologists can test theories and measure cosmological parameters independently from other methods. What voids reveal about dark matter? Voids provide unique insights into dark matter's properties and distribution. First, voids confirm dark matter's existence and gravitational dominance. The formation and evolution of voids depends critically on dark matter. Without dark matter providing the gravitational framework, structure formation would proceed differently.
Studies of void galaxy rotation curves, how fast stars orbit at different distances from the galactic center, reveal dark matter distributions in these low-density environments. The results are consistent with dark matter models developed from cluster observations, showing dark matter behaves the same way regardless of environment. Third, voids constrain alternative theories. Some physicists have proposed modifying gravity instead of invoking dark matter. These modified gravity theories must explain all observations that dark matter explains, including cosmic structure. Void properties provide stringent tests. Modified gravity theories predict different void formation and evolution compared to dark matter models. Detailed observations of voids, their abundances, and their internal structure have ruled out several modified gravity alternatives. Fourth, voids probe dark matter's interaction properties. If dark matter particles interact with each other beyond gravity, if they can collide or annihilate, this would affect structure formation, particularly in low-density environments like voids. Observations of void properties constrain how strongly dark matter can self-interact. So far, observations are consistent with cold dark matter, particles that move slowly and interact only through gravity. But voids provide a testing ground for alternative dark matter models, like warm dark matter or self-interacting dark matter. What voids reveal about dark energy? Perhaps most importantly, voids provide unique laboratories for studying dark energy. Dark energy is the mysterious substance causing cosmic expansion to accelerate. It makes up about 68% of the universe's total energy density, yet we don't know what it is. Leading candidate is the cosmological constant, energy intrinsic to space itself, but other possibilities exist. Voids are especially valuable for studying dark energy for several reasons. First, voids are dominated by dark energy. In clusters and filaments, matter density is high and gravity dominates dynamics, but in voids, matter density is low. Dark energy, which has constant density everywhere, becomes relatively more important. This makes voids sensitive probes of dark energy's properties. Second, voids evolve differently depending on dark energy's nature. If dark energy is a true cosmological constant, voids expand at a rate determined by that constant. But if dark energy is dynamical, varying over time or space, void expansion rates would differ. By measuring how voids expand and how their properties change over cosmic time, astronomers can test whether dark energy is constant or evolving. This is difficult in dense regions where gravity complicates the picture, but voids provide cleaner environments. Third, void statistics constrain dark energy parameters. The abundance of voids at different cosmic epochs depends on dark energy's equation of state, the relationship between its pressure and density. More negative pressure causes faster acceleration, affecting how many voids form and how large they grow. Large galaxy surveys like the Sloan Digital Sky Survey have mapped millions of galaxies and identified thousands of voids. By analyzing void statistics across cosmic history, cosmologists extract constraints on dark energy parameters that complement constraints from supernovae, cosmic microwave background, and gravitational lensing. Fourth, the Alcock-Paczynski test uses voids to measure cosmic expansion. This test compares the apparent size of voids in different directions. Due to cosmic expansion, a void's appearance depends on viewing angle. By measuring these distortions, astronomers can constrain the expansion history and dark energy properties.
Voids have revealed that dark energy behaves consistently with a cosmological constant across billions of years. No evidence yet for evolution or variation. This doesn't prove dark energy is a constant. Other models could mimic constant behavior, but it significantly constrains alternatives. Voids and the cosmic microwave background. Voids also connect to observations of the cosmic microwave background through an effect called the integrated Sachs-Wolf effect. The CMB is radiation from 380,000 years after the Big Bang. As this radiation travels through the universe, passing through regions of varying gravitational potential, its energy changes. Photons climbing out of gravitational wells lose energy and redshift. Photons falling in gain energy and blueshift. In a universe with only matter, these effects would cancel perfectly. Photons lose energy falling in and gain it back climbing out. But in a universe with dark energy driving acceleration, the cancellation isn't perfect. The gravitational wells change as photons travel through them. Specifically, as voids expand due to dark energy, they create regions of decreasing gravitational potential. CMB photons passing through expanding voids gain energy. This leaves a slightly warm imprint on the CMB in the direction of voids. Conversely, as matter clusters grow denser under gravity, though dark energy slows this growth, they create deepening gravitational wells. Photons passing through lose energy, creating cold spots on the CMB. This integrated Sachs-Wolf effect has been detected by cross-correlating CMB maps with maps of cosmic structure showing void locations. The signal is small, temperature variations of only a few microkelvin, but statistically significant. The detection confirms dark energy's influence on cosmic expansion and structure growth. It provides independent evidence for dark energy beyond supernovae observations, linking the early universe, CMB, to late-time structure, voids. Some astronomers have investigated whether supervoids, exceptionally large voids, could explain certain anomalies in the CMB, like the cold spot. While individual supervoids cause detectable effects, they don't seem sufficient to explain the largest CMB anomalies, which likely have different origins. The void galaxy population. Galaxies that reside in voids, void galaxies, have distinctive properties that reveal how environment affects galaxy evolution. Void galaxies tend to be smaller than galaxies in dense regions. They're often late-type spirals or irregular dwarf galaxies rather than large ellipticals. This makes sense. There's less matter in voids to build large galaxies, and lower density means fewer galaxy mergers. Void galaxies are often bluer, indicating ongoing star formation. In contrast, cluster galaxies tend to be redder, having exhausted their gas supplies or had gas stripped away by their environment. Void galaxies, isolated from disruptive interactions, retain their gas longer and continue forming stars. Studies show void galaxies have higher gas fractions. More of their mass is in gas form rather than stars. This gas can fuel star formation over extended periods. Some void galaxies are still actively forming stars today, while galaxies in clusters stopped forming stars billions of years ago. This reveals environmental quenching, the suppression of star formation in dense environments. In clusters, galaxy interactions, gas stripping by hot intracluster medium, and mergers can shut down star formation. In voids, these processes are absent or weak, allowing gentler evolution.
Void galaxies also tend to be isolated. They have fewer neighbors and rarely experience mergers. This means their evolution is primarily internal, driven by their own gas supply and star formation, rather than externally driven by interactions. Despite these differences, void galaxies follow the same fundamental scaling relations as other galaxies. The Tully-Fisher relation, connecting rotation velocity to luminosity, works in voids as in dense regions. This suggests underlying physics, dark matter halos, gas cooling, star formation, operates the same way regardless of environment. The existence of void galaxies also constrains structure formation. If voids were truly empty, devoid of any dark matter, galaxies couldn't form there at all. The presence of void galaxies indicates that even under-dense regions contain enough dark matter to form galactic halos. Void dynamics and cosmic flows. Voids aren't static, they're dynamic systems participating in large-scale cosmic flows. On the void boundaries, galaxies aren't at rest. They're flowing outward, repelled by the void's lower-than-average density. Meanwhile, galaxies in filaments flow toward clusters, attracted by higher density. This creates a network of cosmic flows, galaxies streaming through space in complex patterns determined by the gravitational field of the cosmic web. These flows affect how we observe galaxies. A galaxy's redshift combines two components: cosmological redshift from cosmic expansion and peculiar velocity redshift from the galaxy's motion through space. By measuring both and separating them, astronomers map cosmic flows. Void outflows contribute to these large-scale velocity fields. Galaxies at void edges move outward at hundreds of kilometers per second, creating systematic patterns in galaxy velocities. Studies of these patterns reveal the underlying mass distribution, including dark matter in and around voids. Void expansion itself is a form of cosmic flow. Voids expand faster than the cosmic average because they're underdense. This expansion rate depends on the balance between matter, slowing expansion through gravity, and dark energy, accelerating expansion. Measuring void expansion rates thus constrains cosmological parameters. As voids mature, they grow and merge. Small voids combine into larger ones, just as dark matter halos merge to form larger halos. The void merging process is less violent than galaxy cluster mergers. There's less matter to collide, but it shapes the evolving cosmic web. Future observations tracking void evolution across cosmic time will reveal how structure growth has changed as the universe transitioned from matter domination to dark energy domination. This provides a direct probe of dark energy's influence on cosmic history. The role of voids in cosmic evolution. Stepping back, voids play essential roles in cosmic evolution beyond just being empty spaces. Voids serve as reservoirs of pristine material. The gas in voids is less processed than gas in dense regions. It hasn't been cycled through generations of stars as often. It hasn't been heated by supernova explosions or active galactic nuclei. Studying void gas reveals conditions more similar to primordial gas from the early universe. Voids may influence reionization, the process when the first stars ionized hydrogen in the early universe. The ionizing radiation from early galaxies propagated through space, ionizing surrounding gas. The topology of the cosmic web, including void structure, affected how ionization fronts spread. Understanding voids helps model this crucial epoch. Voids regulate large-scale gas flows. Gas doesn't just sit still, it flows from voids toward filaments and clusters driven by gravity. This flow transports material from underdense regions to overdense regions, feeding galaxy formation in high-density areas. Simulations show these flows are significant for understanding how galaxies acquire gas. Voids also provide relatively clean environments for certain observations. Because voids contain few galaxies, they have less contamination from foreground or background sources. This makes them useful for observations requiring clear lines of sight, like studying the intergalactic medium through quasar absorption lines. In the far future, voids will dominate. As dark energy continues driving acceleration, cosmic expansion will accelerate indefinitely. Distant galaxies will accelerate beyond our cosmic horizon, disappearing from view. Eventually, only gravitationally bound local structures, our local group of galaxies, will remain observable. Everything else will have receded beyond our reach. In this far future, our local group will find itself essentially in a void, an empty space surrounded by matter from which all other structures have disappeared. Understanding voids today gives us a preview of the universe's ultimate fate. Observational challenges and surveys. Studying voids presents unique observational challenges. Defining void boundaries precisely is difficult. Unlike clusters with clear concentrations of galaxies, voids have gradual transitions from underdense interiors to denser walls.
Different algorithms for identifying voids give somewhat different results. Cosmologists have developed various void-finding algorithms. Some look for spherical regions with minimum galaxy counts. Others trace the density field and identify local minima. Still others use geometric techniques, analyzing the distribution of galaxies. Each method has strengths and weaknesses. Large galaxy surveys are essential for void studies. Finding and characterizing voids requires knowing the three-dimensional positions of millions of galaxies. Surveys like the Sloan Digital Sky Survey, the 2-degree field galaxy redshift survey, and ongoing surveys like DESI, Dedicated Energy Spectroscopic Instrument, provide the necessary data. These surveys measure galaxy positions and redshifts, how much their light is stretched by cosmic expansion. Redshift serves as a proxy for distance, allowing astronomers to map galaxies in 3 dimensions. With millions of galaxies mapped, voids emerge clearly in the distribution. Future surveys will go deeper and wider. The Vera Rubin Observatory will observe billions of galaxies. The European Space Agency's Euclid mission will map cosmic structure across cosmic time. These surveys will identify voids at different epochs, revealing how void properties evolved. Studies of the Lyman alpha forest, absorption lines in quasar spectra, probe the intergalactic medium in voids. This reveals the distribution of neutral hydrogen gas, providing information about voids at smaller scales than galaxy surveys can probe. Simulations remain crucial. Observational data must be compared to theoretical predictions. Cosmologists run massive computer simulations modeling billions of particles to predict void properties in different cosmological models. Comparing simulated and observed voids test theories and constrain parameters. Closing. Cosmic voids, vast empty regions spanning hundreds of millions of light-years, are far more than just boring gaps between galaxies. They're fundamental features of the universe's large-scale structure, revealing profound truths about cosmic evolution. Voids formed from tiny density fluctuations in the early universe, amplified over billions of years by gravitational instability. Their formation and evolution depend on dark matter providing gravitational structure and dark energy driving accelerated expansion. By studying voids, we probe both these mysterious substances. Voids tell us the universe has structure on the largest scales, the cosmic web of filaments, walls, and voids. They show us that environment matters for galaxy evolution, with void galaxies differing systematically from cluster galaxies. They provide laboratories for testing cosmological theories and measuring parameters. Perhaps most importantly, voids remind us that absence can be as informative as presence. Empty space isn't featureless. It has structure, dynamics, and history. The patterns of what's not there reveal the forces that shaped what is there. As we map more galaxies, identify more voids, and study their properties across cosmic history, voids continue to yield insights. They're teaching us about dark energy's nature, cosmic acceleration's history, structure formation's details, and the universe's ultimate fate. In the next time you think about the cosmos, remember the voids. Remember that most of the universe is empty space, and that this emptiness itself is a cosmic structure shaped by the same physics that creates galaxies and stars. In understanding the voids, we understand the universe. Thank you for exploring the cosmic emptiness with me. If you found this journey valuable, subscribe for more deep dives into cosmological structure and the forces shaping our universe. And leave a comment. What surprises you most about cosmic voids? Keep exploring, keep questioning, and keep marveling at the universe's structure, both the matter and the emptiness.